recall that when we are talking about differential equation points, first we write them in standard form. An ordinary point is a point where px and qx are both analytic, specifically written in polynomial form. Otherwise, if they are on the denominator of px and qx, we call them singular points. You have a regular singular point, you have irregular singular point. For a regular singular point, you need to multiply px by x minus x sub 0 and multiply qx by x minus x sub 0 to the second power. If both of these are analytic, then you have a regular singular point, otherwise you have irregular singular point. Take a look at this differential equation. 3x, the second derivative of y, plus y prime minus y equal to 0. First, write it in standard form. It means that divide by 3x. So 3x divided by 3x, the second derivative of y plus 1 divided by 3x y prime minus 1 divided by 3x y equal to 0. You get the second derivative of y plus px, which is 1 over 3x, and qx, which is negative 1 divided by 3x. Multiply px by x, you get 1/3, which is analytic, it's just a constant, and then if you multiply qx by x squared, you get x squared times negative 1 divided by 3x, or minus x divided by 3, which is a polynomial, so it is analytic. So x equal to 0 is a regular singular point. Now, since you have a regular singular point, to find the solution, you're going to apply Frobenius theorem. It means that the power series that you're going to use have the following form. Let's take the first derivative and second derivative of power series of Frobenius form and then substitute that in the original differential equation. When you substitute these three into the original differential equation, it is 3x times the summation of n plus r minus 1, cn x to the power n plus r2, then minus 2. So take a look at this. You have another x here. So when you combine this x and the exponent, negative 2, it becomes negative 1. Plus, here you have y prime. Just take this y prime and substitute it here, minus y, which is the summation of cn x to n plus r. Now we try to combine these together. For the very first two power series, both of them starts at 0 and the exponent are n plus r minus 1. So you can easily combine the first two power series into one power series. The last power series, n starts at 0 and the exponent is n plus r. So what are we going to do? We're going to make a little bit of adjustment. First, factor out x to the power r. X to the power r is common in both of these. And then you can just plug in 0 and find the 0th term here. So you get r, which is 0 plus r, times 3 times 0 plus 3r minus 2, c sub 0 x to the power 0 plus r minus 1. And remember that you factor out x to the power r, so there is no r left here. For the rest of the terms here, since you are looking at larger terms, you can do the adjustment. So define k to be n minus 1. Again, guys, n goes to infinity. So these are our larger terms. And for the last power series, use k equals to n. It helps to combine these together and find a recursive relation here. So again, x to the power r is factored out, and then you have r, 3r minus 2, c sub 0, x to the power negative 1, plus, when k is equal to n minus 1, n becomes k plus 1. So you can just substitute that here, and then combine these two power series together to find the recursion. Very good. So take a look. This guy, if you set it equal to 0, you get r times 3r minus 2, c sub 0 equal to 0. Here you have x to the power negative 1. We don't care about that one. The coefficient must be equal to 0. So it means that r is 0, or r is equal to 2/3, as you can see here. And now if you set this equal to 0, this is this recursive term, k plus r plus 1, 3k plus 2, 3r r plus 1, ck plus 1 minus ck equal to 0. So you can write down ck plus 1 in terms of ck. Then you're going to substitute r equals to 2/3. Then you're going to substitute r equals to 0 to find the relation between k and k plus 1. Now, if you plug in some values, for example, if you calculate for c sub 1 from the very first term is equal to c sub 0 divided by, wherever you see k, you're going to substitute 0. 3 times 0 plus 5 times 0 plus 1. So you get 5 times 1. C sub 0 divided by 5. The second term from the first recursive relation is C sub 1 divided by 8 times 2, or C sub 0 divided by 2 factorial 5 times 8, and so on. If you plug in R equal to 0, this is the recursive relation that we have. We're going to list some of the initial terms to try to see if we can find a nicer pattern here. Sometimes it's easy to find a nicer pattern. Sometimes it's difficult. Some other times you don't see any pattern. So basically you have two power series solution and they're written this way. In summary, you have the differential equation. First, you need to check to see if it's a regular singular point or if it's just an ordinary point. When it's a regular singular point, you're going to apply Frobenius theorem. Identify what is R, and then plug that in to the recursive relation, and then try to find a pattern. After you find a pattern, you can write the power series solution this way.